On the left is the Summit supercomputer at the Department of Energy's Oak Ridge National Lab. I've been there with Summit. We used it as part of the Google quantum supremacy demonstration in 2019. We actually ran a smaller version of the supremacy experiment on Summit to benchmark it, to look at the energy consumption, the time required to run it, and concluded that an estimate was it would take hundreds of thousands of years to run the exact same quality of simulation on a supercomputer like Summit as you could run on Sycamore in 300 seconds and do millions of samples of that quantum simulation. Summit was retired last week. I saw the news. I was a little bit sad to see that it's been taken offline, but Frontier has been working for a couple of years already, and there's more planned. And we'll talk a little bit today about DOE's plans and how quantum computing is going to play a role there. In the middle is a typical data center used by companies around the world to process their data, store their data, respond to internet queries, stream movies in 4K. And the colors from a lot of the fibers that are used, that optical fiber is performing the classical networking, allowing the data to flow quickly around between the different processors, which are a mixture of co-processors, GPUs, graphics processing units, and CPUs, computational processing units. So these two are the main chips powering the AI boom that you're hearing about and seeing in the world. And on the right is a picture of the Google quantum computer, the chandelier, as they call it. You can see the wires at the bottom. An example of an order of 50 or 100 qubits. There's a number of companies around the world, and these quantum computers really promise to revolutionize how we do computation, and probably the largest revolution since the transistor. So this pace of evolution is only accelerated, and now there's going to be a merger and a unification of these multiple co-processors working together. Let's talk a little bit about how they're different, how they're similar, and some of the strengths of them. So data centers are used for large data applications, large memory requirements, doing matrix multiplications. So generally low-cost compute, but a lot of similar computations. You're running the same. You're scrolling on Instagram. You're sending a message, watching a movie. And people watch generally the same version of movie that's stored on the data center and streamed to you wherever you are. And so it's generally many simple computations that happen again, a lot of similar computations using a lot of the same data that's stored in the cloud that provides this low-cost compute around the world. Supercomputers are also big data devices. They have large memory, but they have very specifically designed combinations of GPUs and CPUs today. Whereas data centers have racks of GPUs and racks of CPUs, you're seeing a bit now the latest GPUs from NVIDIA, the A100, and then Blackwell is coming soon, have actually GPUs and CPUs on a chip that they call a compute resource. So there is a little bit of a blurring there where now you're seeing data centers are having blades of processors that are actually co-processors. But supercomputers are built, there's a snapshot in time taking stable generation processor units that are actually custom designed into a blade that goes into a rack. They have very fast memory, specifically designed, multiple tens or hundreds of gigabits per second. Classical optical networking that routes, and they're used when you need to run large number of computations very quickly. There could be a lot of iteration, recursive functions that are being called. So that fast networking allows you to route the data, and they're well planned. So users book time on a supercomputer like Summit or Frontier, and they access it, and they've already in advance decided on what they want to compute and the algorithms they run. It could be for weather modeling, could be for risk assessment in finance, it could be for nuclear physics modeling, it could be for climate change, etc. And those are run, could be multiple users at the same time, or one user could use the entire facility like we did at Google with the quantum supremacy benchmarking. So the keys there are fast networking, stable, custom designed blades of co-processors, GPUs and CPUs, but they have a finite lifetime. Generally, supercomputers run for 3 to 5 years, and then they're retired, recycled, and a new generation of supercomputer comes online. Quantum computers have more in common with supercomputers in that the applications they target tend to be where you're looking for really highly structured data. They're not a large data application, quantum computers, because of the limited fan-in, fan-out from the qubits on the chip couple hundred, for example. They're really good when you have exponential scaling of the mathematical equations describing a physics, which could be chemistry or optimization, etc. So they're really useful for simulations. Quantum simulation is very natural for quantum computers because that's what they are. They are a quantum device themselves. They're really good when there's not a known mathematical model, but there's highly correlated complex data. But they're more of a small data set. You can see there's overlap in here, there's similarities, but there's also specialties. And so users will choose to run in a data center or in a high performance compute facility or with a quantum computer. But really in reality, algorithm developers, application developers want to be able to access these resources and put them in combinations to really solve their problem as fast and cheaply as possible.